Hello everyone. So I, Rajat Kumar and Madhvi Agarwal are working on the paper and efficient methodology wave of margin timing violations in digital circuit using machine learning under supervision of Dr. Sneh Saurabh. So in this paper, we are trying to solve the problem of timing closure, which is very severe at advanced process nodes. So we encounter numerous margin timing violations at the sign off stage. We fix these violations by making design changes, which in turn incur a lot of penalty area, power, turnaround time, and other figures of merit. However, many of these margin timing violations arise due to the artificial pessimism, which is considered during the modeling of the flip-flop. So we can simply waive off these timing violations. So through this work, we are trying to remove the pessimism in the traditional history, which ignores the dependencies of the setup time, hold time, and the clock to queue delays. We use the ANN based model to efficiently compute the CTQ delays. And thirdly, we transfer the surplus slack, which is present from the output side of the flip-flop to the input side, so as to consider the violation as waived. So traditionally, the timing model of flip-flop is modeled by setup time, hold time, and clock to queue delays independently. So spice simulations are performed for each flip-flop, and relevant timing information is stored in the library with setup time, hold time, and CTQ delays as separate two-dimensional lookup tables. So while characterization of setup time, we consider the counterpart hold skew to be very large, and for the hold time characterization, we consider the counterpart setup skew as very large. So this basically introduces the pessimism in the timing model. So in previous papers, we see different approaches. Likewise, we see various SHPR techniques have been exploited, flexible flip-flop timing models have been prepared. But basically, these techniques do, they reduce the design size and design effort, but they compromise on accuracy. So and they do not exploit inherent degrees of freedom. But through our ANN model, we exploit the freedom degrees of freedom much accurately, and we do not compromise on accuracy. So now comes the methodology. So for our methodology, we define certain basic definitions of rise skew, the rise delay, setup skew, the hold skew. So for this, we simply use this D flip flop with the CP and the Q pins, where the CL load attached to the Q pin. So then we consider UST, LST, that is pursuit threshold, which is 80%, low slew threshold, which is 20%, and the daily threshold, which is 40% for our definitions. So this is the TD rise, this is TC rise, the tau is setup skew, tau which is the whole skew, and TCQ rise is the delay. So now we capture the effects of CTQ delay on these parameters. So as mentioned previously, these dotted lines here simply show the CTQ modeling of the traditional models. So for which, likewise, to capture the dependency on the setup skew, we consider the whole skew to be large. So here we see that whole skew is large at 63 picoseconds, and we can see the CTQ delay is captured to be the minimum for this. Similarly, for the case of whole skew, we consider the setup skew to be large for the traditional models, and similarly here also the CTV line is the least one line. So now to capture further to capture dependency on the load capacitance, data slew, and the clock slew, we divide it into four parts. That is the setup and hold is large, setup is large, hold is small, setup skew is small, hold skew is large, and setup skew is small and hold skew is small. So these lines, various lines show the dependencies of the CTQ on the various parameters. And the dotted line show the dependencies in the case of the traditional model. So we can easily see the difference. So we need to capture these dependencies to train our model efficiently. So as we can also see that when the setup skew and the whole skew are small, we can see that this CTQ delay is rising exponentially. So to capture this exponential increase, we take the in this region we take very fine steps, and while characterizing, we vary all these five parameters, and such that the flip flop till until unless the flip flop fails to dash fails to dash the data. So this way the characterization is done, and then we simply move to the once we characterize this, we feed this to the spice netlist and the virtuoso through the virtuoso ADLE tool. We generate the data in the form of CSV format, and then we move to the ANN model. So now for our ANN model, we have considered ANN model of 5 layers. that is 5 since 5 in the first period, that is the input features, that is all the 5 input features, and then subsequently 28, 28, 25, and the one that is the output feature. So basically these are decided as per the accuracies. So this is the adjusting the hyperparameters by adjusting hyperparameters. So now we consider for ANN model, we simply feed 80% data as a training data and 20% data as a tested data. And then we simply see an application of our model on the real world design, that is S1196 design taken from the Tau contest 2019. And we perform swim simulations on 15 nanometer and gradable cell libraries and using NCSU free PDX models. So as we can see here in this part, we have 3 flip-flops. So we can see that this is 549, there is positive slack of 0.6 picoseconds, and there is a violation at instance 560 and 563. So further, traditional models shows that there is a 22.2 picosecond CT2 delay and 12.9 picoseconds. But actually, since data transition is taking very close to the edge, so we can see that Spice shows the actual increase in the CT2 delay, which is 22.7 picoseconds and 13 picoseconds. Further, we can see that proposed model has also predicted the same delay as the ANN, which is here in the case 18.5, 22.5, 30. Hence, our model is very accurate with respect to the Spice. And so further, we can see that maximum allowed delay, which is for our case, we have taken theta as 10%. That is the degradation allowed from the nominal delay. So here we can see that we can increase, we can tolerate this delay up to 20.34 picosecond, 23.04 picosecond, and 13.4 picosecond. So we can simply see that here there was an increase of 0.5 picoseconds, and here there is an increase of 0.1 picosecond. So in all, there was a total increase of 0.6 picoseconds, and since there is a surplus lag of 4 picoseconds at the G546 stage, so we can transfer the surplus lag to simply waive off these marginal timing violations. So hence, our model shows that these violations can easily be waived off, and so we can use this model to waive off the violations. Now comes the conclusion. So we can simply conclude that we can use our ANN model to simply compute the CTQ delay sufficiently, wherein we can incorporate all the 5 parameters on which the CTQ exactly depends. That is these setup skew, hold skew, load capacitance, data skew, and the block skew. Then we can simply transfer the surplus slack on the output side to the input side, considering our model. And here there is a one-time characterization effort required. And further, we can use this RAN model to over many designs. And we can also reduce the characterization effort by simply intelligently selecting the data points and existing hyperparameters for a better ANN. So these were our references. Thank you.